All right, welcome everybody. My name is Evan Shapiro and I'm a co-founder and CTO of Sofar Ocean. And today I am joined by Austin Vincent from PME and Chris Verlinden from AOS. And we're going to be sharing some exciting new developments. These are products that are going to be added to Spotter's ecosystem of compatible sensors and also the Bristlemouth ecosystem. If you're new to both of those things, we'll talk about them as well in this. But first, I want to back up a step and talk about why we're here. So at Sofar, our mission is to connect the world's oceans for a more sustainable future. We're really focused on scaling ocean sensing applications. We want to put lots of sensors in the water. We want to collect lots of noisy, impossible data, and we want to distill that into insights that will help us make better decisions across industry, government, and resource management. And so we're on track to do that. We develop things very quickly at unprecedented scales for marine technology. We have groups like PME and AOS who have deep expertise in the many niches of ocean sensing that are required to measure and understand our oceans. But we run into a tired old issue. And it is one that is a little difficult to gain empathy for if you haven't experienced it yourself. So I want everyone to do a little exercise with me, even close your eyes if you will, and imagine that you're buying a new mouse because you are sick and tired of your old crusty one. And so you go into Amazon and there's all these options and you pick the one you want. It magically shows up on your doorstep the same day because of robots and automated logistics. And you open up the box and you see a mouse with some bare wires hanging off the end of it and a 300-page technical manual that tells you how to solder it into your computer and write some code so that it can start working. While that sounds ridiculous to our modern experience, it is unfortunately the world that we live in marine technology. We have a whole plethora of different connectors and protocols and power distribution standards. Some of them seem the same, but they're not actually interoperable. And if you plug them together, you would break your stuff. When you want to connect something like a sensor that's designed to be plugged into a platform, it always requires engineering, and it shouldn't. And it is a huge hindrance to building scalable systems because now everything's a one-off, everything is niche, and every time that we want to take these off-the-shelf components that we've invested decades into perfecting and plug them together in a novel configuration, it's another years-long engineering project. And it shouldn't be that way. It should be as simple as USB, where you can buy things that are intended to be connected, you plug them together, and they just work. Imagine if we did have that. There's no reason that we shouldn't have that in this industry. Yes, it's smaller than things like consumer electronics. Yes, it's harsher than things like automotive. But if we can get the right organization around it, the right cooperation and consortium in the industry between groups that are producing things at scale, there's no reason that we cannot have broadly adopted compatibility standards that allow these plug and play experiences for the users who are building and scaling sensing applications. And so we set out to build that. We, Sofar Ocean, partnered with a range of organizations across industry and government and philanthropy and venture to develop and introduce and foster the adoption of an open, fully open source connectivity standard designed for marine sensing and robotics applications. And it's called Bristlemouth. I won't get into the technical details, but it is a very low cost and extremely broad set of capabilities standard. So it's designed to work anywhere in the ocean and deliver all the power and data that an application would need. And it's a universally compatible connector. So any Bristlemouth compatible things can be plugged together without any engineering work. What we started with was really focusing on community adoption. So this is going out to groups to understand how they're developing sensors and integrating systems. This is building development kits and online forums and support. Over 100 developers have created dozens of contributions in this open source Bristlemouth ecosystem community, and it's continually growing and going. We have some really exciting developments that are coming out of this, like cameras and chemical sensors. But at the same time, to build this open ecosystem of compatible modules that can be scaled in marine sensing applications, we also need industry adoption. And so this is what we're at the cusp in. This is what we're going to be talking about today, which is really exciting. Sofar Ocean, earlier this year, has fully committed to Bristlemouth. So every product that we manufacture, design, and make, everything that we ship is Bristlemouth capable, and everything that we build in the future will be Bristlemouth capable. This includes our spotter platform, which provides wave and wind sensing, surface weather measurements, and then telemetry and power. And today, this ecosystem is expanding with the announcements from PME and AOS, who are building natively Bristlemouth compatible modules. So these modules will be able to plug and play into any Bristlemouth enabled spotter platform, but they will also be able to plug and play into any other Bristlemouth enabled platforms in the future. So with that, I am going to hand it off to Austin Vincent from PME to talk about and introduce the dissolved oxygen sensor that they are currently developing and will be releasing next year.
Thank you, Evan. Great intro. Hey everybody, Austin Vincent here, product specialist with PME, short for Precision Measurement Engineering. And excited to talk a little bit about our dissolved oxygen integration. As Evan mentioned, a lot of integration in this industry can, produce headaches and just a lot of, engineering in the background. So we're just looking forward to discuss this integration with you all today. A little bit of background here. So PME was founded in 1982 by Dr. Michael Head, who received his PhD from UCSD Scripps Institute of Oceanography. And it really was started in the garage, one of those fun stories. But it's grown over 40 years, and we have now worked with over 150 universities. Our products are in over 30 countries, and we work with a variety of customers from government agencies to the energy sector. We've been growing our aquaculture portion of the business, tribal communities, private nonprofit research, and then climate, freshwater, and marine science. So freshwater, ocean, doesn't matter, we have instruments deployed. And we really recognize the importance of reliable water quality data, especially as it pertains to research. Our team is focused on developing high quality products that are affordable to use, or affordable, easy to use, and long lasting. Perfect. So why PME? It's probably a question on everyone's mind. There's a lot of companies that measure, record data for dissolved oxygen. I mean, it's an essential piece of life. Fish need it, humans need it, even down to microorganisms. But PME has developed a dissolved oxygen sensor that is really easy to use. It's incredibly accurate, plus or minus 5%, and it's relatively low cost. We have specialized in this sort of single parameter approach, and with that, we're able to be experts in the field as it pertains to dissolved oxygen. A little bit about the sensor, again, is highly accurate. There's an extremely stable calibration, super durable, and a long life cycle. A big value proposition of the sensor is its low power consumption. Every time the sensor takes a sample, it only flashes on for just a millisecond. So these sensors can last for years on a single charge. The power source in this case will be external, but our in-house sensor, the mini dot, is powered by 2 AA lithium batteries, and it's rated for 500,000 samples. So just to give you an idea, 2 AA batteries will be rated for 500,000 samples, and I mean, you would have a hard time reaching the battery life limit in that case. There's a small form factor here. As you can see in this diagram, it's just a few inches long. Extremely budget friendly. Again, as we focus on a single parameter approach, There's a little bit less frills involved, so we're able to cut costs and really focus on high value add and really accurate data. As far as depth rating, it's currently rated and pressure tested for 100 meters, but our mini dot is rated for 300 meters. So we know there's some room to play there, and we're looking forward to increasing that depth rating as we continue testing this product. It uses the same optical DO sensing technology as our mini dot. So really it's a proprietary optical oxygen sensor that was developed in-house, and it has over 14 years of field use and validation. And since 2010, we've sold over 12,000 mini dot units, and it's been extremely well received by the environmental science community. So I'm sure you're wondering, what about biofouling? Now, as we know, the ocean is a pretty harsh environment. We're not in a clear, frigid, pristine alpine lake. There's a lot of factors at play in the ocean. So we, along with Sofar and Bristlemouth, have decided to integrate an anti-fouling wiper into our dissolved oxygen integration. This has been validated with our mini dot system. We've essentially brought all our experience from the mini dot and wiper into this integration with the Bristlemouth, so it's been proven, field tested, and validated. There's been months of effectiveness demonstrated. We've had researchers deploy mini dots with a wiper for over a year and come back, and the entire system is overtaken by biofouling, but you'll see that little center spot is still clean and recording clean, accurate data. We have a patent pending anti-fouling mechanical combination, and it's really kind of hard to replicate. We've seen some competitors in the space, and in our opinion, no other market solution really compares. So we are excited to integrate that, and really allows a little bit more peace of mind for these long dwell deployments. So as we started this partnership, we sat down and really wanted to focus on some key features, some KPIs, if you will, of this integration and what really matters most. So I'll run down, it's a bit of a laundry list, but really every factor here is extremely important to the success of the integration. So the dissolved oxygen integration is Bristlemouth native, and it can connect to other Bristlemouth devices. As I mentioned, it's long dwell capable, so if you're deploying a spotter buoy system with our dissolved oxygen integration, at least expect 1 or more years of clean, reliable, accurate data. As I mentioned, the integrated anti-fouling wiper for extended deployments really adds a little bit of peace of mind. And again, the low power draw really lends itself to these longer deployments. Size efficiency and containing and capturing the correct output data. I mean, these are kind of necessary prerequisites, but we really wanted to emphasize that you are going to get accurate, reliable data even in these harsh environments. The sensor is remotely configurable, which is huge in the space that we're playing in right now. And in addition to dissolved oxygen, it outputs data for temperature. So that is a nice little added bonus. We can seamlessly implement secondary sensor data to generate DO saturation percent. And we have a formula if anyone's interested to know how we arrive at that saturation percentage. Everything has been documented and supported by PME along with Sofar and Bristlemouth during this process. So if you have any questions, I'm sure anybody from those 3 teams will be able to help. So we have a mock-up here on the far right of what it might look like. We've gone through a few iterations, and we're almost to the final form factor, but that is a pretty good rendering of what the final form factor might look like. And it's, we're unlocking the next generation of real-time water quality sensing. It's the first turnkey real-time DO sensor designed for long dwell monitoring, especially in the ocean. A lot of companies in the space are focused on fresh water, and as are we, but we've really started to pivot into more of a saline environment, especially marine coastal applications. Its smaller size and lower power requirements makes it extremely easy to integrate and combine with other instruments, for these complex multi-parameter type research projects when combined with other sensors. And again, as previously mentioned, we really lean into the fact that it's incredibly robust, compact, accurate, and affordable. So we do more than DO, but we really focus on DO, and we consider ourselves to be experts in that field. You can set alert thresholds and receive those alerts in real time for operational decision making, depending on what your goals are. And when combined with data, as far as surface data with waves, winds, and barometric pressure, and subsurface data such as temperature, currents, and pressure, you can get a full view of the ocean state. Here is a rendering. I know I showed you one earlier, but here, as you see in the bottom right corner, there is the wiper integration. In the bottom left, you have the actual sensor, which is a membrane, and then the actual sensor spot there is silicone, and that is where the water passes over and the measurements are taken and then logged. And then here's a top-down version, bottom left, where you can see where the wiper would keep the sensor spot clean. And then finally, top right, you have the plug and play compatibility, which will work nicely with the Bristlemouth open standard. Okay, spec sheet. I know many of you are likely, technical in the sense that you like to know how it works, as far as the accuracy, resolution, etc. I'll touch on a few here. I won't go down the list, but my favorite specs are the plus or minus 5% of accuracy, the resolution of 0.001 milligrams per liter, as it pertains to the oxygen resolution. Unlimited memory. I get a question from time to time, what does that mean? How can it be unlimited? Well, technically it's not unlimited, but it would take you thousands of years to reach the limit as it relates to the internal SD card. So we just like to say unlimited, and we believe that to be true. And then finally, the depth rating of 100 meters. This is kind of a variable metric, if you will, and we are looking to increase that as we complete further pressure testing for the device. And thank you for listening to my portion. Here's a little bit of info as far as PME. PME.com, info@pme.com. You can reach us if you have any questions as far as the integration. And with that, I will pass it over to Chris Verlinden, PhD and CTO of Applied Ocean Sciences, and looking forward to hearing a little bit more about the Hydrophone integration into the Bristlemouth open standard.
Thanks, Austin. Let's see if the slides will advance. All right. So I advanced too many. The product I'll be talking about today is called Borealis. It's an acronym should you choose to use it, or you can just call it Borealis because it's a cool name. It's the Bristlemouth open recorder and edge processor for acoustic low power information systems. Essentially, it's an acoustic recorder and computer that's designed to work at the edge and burn very, very little power while doing it. I first just want to acknowledge my team at Applied Ocean Sciences who's been working on this. It's not just me. In fact, it's very little me. We have a team of incredibly competent and hardworking engineers. Just this morning, we were deploying 3 of these instruments and had to get up at about 4 a.m. to do it. So these guys have just been burning hard and doing a great job. Our collaborators at Sensor Technology up in Canada, they are a provider of piezoelectric ceramics and transducers and hydrophones. They're awesome. If you haven't used one of their hydrophones, they're my favorite. I'll never go anywhere else now after I've worked with them for a while now. And finally, Sofar, these guys have been super helpful in helping us integrate with the spotter buoys and the whole Bristlemouth ecosystem. So just want to thank all these folks. Before I get started on the sensor, a little bit of background about Applied Ocean Sciences. We're a small 20-person or so shop, started about 5 years ago. We also started in a garage. Now we're in a nice garage. So, we've come a long way as well. Maybe not selling 12,000 sensors, but we'll get there in about 1,000 years at the rate we're going. So I have good confidence that we'll we'll get there, and hopefully the sensor is a part of that. We specialize in ocean acoustics, physical oceanography, chemical oceanography, atmospheric science. We love it when there's a complicated sensor problem where the environment matters and you have to optimize where you put your sensors. And we got very, very excited to work in the Bristlemouth ecosystem because the more sensors there are out there, the more our algorithms and optimal placements and command and control is useful. We were struggling with the lack of low-cost sensors, so the idea for Borealis was born. So let's dive in. The bottom line for Borealis is that there's need for passive acoustic monitoring. The ocean is big, it's hard to sense. It's not very see-through to most of our traditional sensing modalities. Things like optics and RF and, radar and LiDAR and all the DARs, they don't do so well in the ocean. Sound, however, propagates very well in the ocean. So as a result, it's sort of how we see the ocean. We can navigate, we can communicate, and we can, sense the environment, all using acoustics. That being said, existing systems are too expensive for widespread adoption. They're often delicate. I break them myself. I can't be the only one. They're energy intensive. They're computationally expensive to do any type of processing at the edge. Even just running the system can be energetically expensive. They're hard to integrate with existing, infrastructure. Like you've got your own, pointy clicky or user interface or workflow that you're used to using, and a lot of the systems out there, have closed and proprietary systems that make them very hard to integrate. They don't have sufficient endurance. I don't like having to go out every single day to change batteries, especially not in the winter. So, most of the acoustic systems that are out there don't last very long. The quintessential example is the Navy sonobuoy. They last about, 6 to 12 hours. The system we're talking about here, Borealis, will store data for 90 days, but last indefinitely because it burns a heck of a lot less power than the spotter buoy can provide. Finally, it is difficult to implement your own software on somebody else's device. And so that's something that we've been targeting solving with this device. As a small business, in the ocean technology space, I have always found it challenging to introduce new products and new sensors because of, most of the sensors that are out there. Evan's point about the mouse, is perfect. Like, it's exactly right. When you order an ocean sensor, it shows up with wires and, maybe an integration documentation, to tell you how to write your own software to deal with it. And, oftentimes if you use one sensor, you have to use every other sensor from, the same company or the same ecosystem. And that's challenging if I don't want to make every sensor. Like, I understood about half the words Austin said. AOS is not going to be making an oxygen sensor anytime soon. And I don't want to have to make an oxygen sensor so that I can make an acoustic sensor. And so the Bristlemouth standard that we've been developing against solves that problem. It's an open ecosystem that can basically lower the barrier of entry to small businesses like Applied Ocean Sciences, so that we can develop this sensor. So let's talk a little bit about this sensor. Like I said, it's a passive acoustic monitoring device that enables edge processing. And I think I lost the ability to advance the slides, Evan. Do you mind hitting go for me? Oh, perfect. Perfect. So here's a picture of the device. This is one of the ones that we deployed this morning. That's this guy. It's dirty, so I have a nice clean one that didn't go out in the ocean this morning. This guy here as well. The system is a single channel hydrophone, although you can put a second hydrophone on it. The electronics can take 2 channels. That is compatible with the Bristlemouth open data protocols. It is disruptively affordable, we hope, and it is incredibly versatile. It's not necessarily the best hydrophone for finding, whispers 1,000 miles away, and it might not be the best hydrophone for monitoring a volcano from inside the volcano, but it certainly could do everything from environmental monitoring for pile driving to finding whales and baleen whales, toothed whales. It's incredibly versatile, so you can use it for almost any application. It's designed to be deployed either drifting or moored with the spotter buoy or any other platform, that is in the growing Bristlemouth ecosystem. You can optionally also attach temperature and pressure and conductivity probes. Here's a quick schematic of the system. Again, it's just what you're looking at right here. The sensing element is a sensor technology SQ17 hydrophone. It's just a workhorse of a hydrophone. You probably couldn't get a hydrophone with these types of specifications for double the cost almost anywhere else. It's incredibly sensitive. It is robust. You can drop it many times and it keeps working. I've tested that a lot. It's just a really great hydrophone. The rest of the system fits in a 2-inch cylinder that's approximately, I'm going to switch to metric here, about 150 millimeters long. There's a carrier board that holds a moat PCB, which is the interface to communicate with the Bristlemouth, the rest of the Bristlemouth ecosystem. The flip side of that platform has a just standard Raspberry Pi 02W, just the most vanilla Linux SBC you could possibly imagine, with interface documentation so you can write your own detectors, classifiers, software that you want to run at the edge. And then the heart of it is AOS's SCARY, or self-contained acoustic recording instrument, PCBs, which does the analog to digital conversion, all the amplification, as well as low power compute. So in low power mode, and we can go to the next slide, Evan, so we can start talking about some of the stats. The system burns, we're still swapping components here and there, but it's between 23 and 40 milliwatts, which we're really excited about, because it's, that makes it an order of magnitude less than most of the devices we're used to working with. While in that low power mode, not firing up that Raspberry Pi, it can do things like simple energy detectors and ambient noise analysis, decade band level noise, and even send out those reports via the Bristlemouth standard. It can also do exception-based reporting to tell you, hey, something interesting is going on, maybe fire up that more powerful computer and do some additional processing. I think the things that set it apart from other devices is the fact that every interface is open. How every board talks to every other board is something that is just freely available to the public. It is extremely low power, which makes it extremely high endurance. The acoustics are good. It's not a Seawolf submarine, but it also doesn't cost as much as a Seawolf submarine. It's versatile for a variety of applications, which we'll talk about, and it's low cost. I'll pick up just a couple of the stats following Austin's example. The sample frequency default is about 31 kilosamples per second, but you can bump that up substantially higher, definitely well into the 60s, probably up to darn near 100 kilosamples per second. That does affect the amount of memory that's available for computation. The depth rating is currently 100 meters, but that's only because that's how far we've tested it. Every individual component is rated to 950 meters. So we expect that soon we'll be able to expand that. Won't talk about all the gain and things like that. I will say that we are planning on bringing this to market for $2,700, which is less than some hydrophones that are the quality, and it's got all the processing and everything on board. So we're pretty excited about that, and we're pretty proud that we were able to bring the cost down to that point. Let's move on to the next slide. The device is designed to be incredibly versatile, to be useful for everything from marine mammal monitoring, and that's all the marine mammals. That's the baleen whales at the lower frequencies, and toothed whales and dolphins and porpoises at the higher frequencies. This can do it all. It's designed to be used for environmental impact assessments for things like offshore construction, offshore wind, ship shock trials if you're the Navy, maritime domain awareness. Fishing vessels are very loud, so are semi-submersible smuggling vessels. So there are applications to defense and homeland security, and also for the prevention of IUU fishing, and global monitoring of the soundscape. So if you have any questions, that's my email. If you have just general questions or want to learn more about applied ocean sciences, please feel free to reach out to that second email there. And if you need any additional information, I'll post Evan's home address and social security number in the chat, so you can get a hold of him with any follow-ups. Over to you, Evan.
Thanks, Chris. And yeah, folks, don't be shy to give me a call anytime, day or night. So I am really thrilled at the developments that PME and AOS are doing here. When we started this partnership, I didn't have in my mind how novel and compelling these products would be in their own right. This is a new kind of dissolved oxygen sensor that is uniquely suited to long dwell applications. This is a very new kind of hydrophone that has never really existed, even though people have been dreaming about it for years. And so bringing these things to the market, like forget Bristlemouth, that's exciting enough. But when we add on now that these elements are going to be plug and play interoperable with this growing ecosystem, the power of that, the value of that just keeps on compounding geometrically. So remember that spotter and smart mooring are Bristlemouth capable, and so that these developments and anything new that comes along can plug and play into this ecosystem, as well as what is already in this ecosystem, which we have. There are a variety of sensors and a development kit already available that can now be mixed and matched in new applications. And so as an example, this is data from a system that we maintain at our test site off of Ocean Beach, San Francisco in California. We have very interesting tidal systems around the San Francisco Bay Area. There's a tremendous amount of water and nutrient transport that happens through the Golden Gate, and there's a lot of interesting dynamics in the water. And so we have a system that continuously monitors water level and currents and temperature and gives us stratification. And we can see some really interesting data that can feed into tidal monitoring and coastal erosion. We can have these systems scaled in the wild and augment them with hydrophones. And now, along with this flow and navigability, we can monitor for vessels. And so imagine what this could do for fisheries management if we're trying to understand how legal and illegal fishing are operating in an environment around currents and flow and tides. We can add this modular capability to a system to build this very powerful application. Similarly, we could outfit a system that has oxygen stratification. And so now we can focus on modeling flows with a current sensor and surface weather and oxygen stratification. We can understand flows around nutrient transport for mariculture or create harmful algal bloom alerting systems. And that's just the beginning. That's what the elements that we have today. There are more exciting Bristlemouth developments that are coming. Imagine if we did have a hydrophone, a Borealis, on every single one of the hundreds of free drifting spotters that are out in the open ocean. We could truly build this global ocean soundscape, and we wouldn't have to re-engineer a platform to do that. What if one of our largest deployment partners, Aqualink, who focuses on mitigating coral reef bleaching, could put a dissolved oxygen sensor on every single one of their hundreds of systems that are around the world deployed on coral reefs today, monitoring for bleaching events? How valuable would that data be to these researchers trying to save these critically endangered resources? And then as new capabilities emerge, new battery technologies, new ways of harvesting power from the ocean, new telemetry modules. Satellite data today is very expensive out in the open ocean. When we see things like Starlink direct to cell or other new telemetry become available, we can imagine augmenting existing systems with those capabilities. Simply modularly plug and play, take out the old thing, plug in the new thing, and we're off to the races at scale. So if this is exciting to you, there's a couple ways to get involved. One, these systems are available for pre-order today. There is a limited early batch where you will receive the value of the Borealis hydrophone, the PME microdot dissolved oxygen sensor for free. So it's a significant discount on the system. There's not many of these available. They are running out. That ends my my TV sales marketing spiel. If you're interested in these systems more broadly, email us at Sofar Ocean or Chris and Austin at AOS and PME. And if you're excited about Bristlemouth as a standard and you want to understand more of what is out there, if you are developing systems or sensors, please reach out to us. We want to get as many companies and researchers and developers as possible supported and adopting this. Platforms, sensors, thrusters, whatever you've got, reach out to us at info@bristlemouth.org to get the conversation started there. All right, so I'm going to stop the screen share and then we'll turn it over to questions. So folks, you can submit questions in the chat and they'll show up for us. And we've got a few going. So I will, let's see, first off, Austin, if you could tell us about the harmful algal bloom application in a bit more detail. How does dissolved oxygen play into that? What other parameters would be interesting in that application?
Sure. Yeah, so harmful algal blooms, I'm actually at a limnology conference right now in Lake Tahoe, the North American Lake Management Society, and HABs have been brought up time and time again. It's of high importance, not only in the limnology space, but in the oceanography space as well. And as I mentioned earlier, organisms need oxygen to thrive and survive and propagate. But in addition to understanding the dissolved oxygen in that sort of ecosystem, there's some other factors at play. Notably, chlorophyll, temperature, and light. And these all kind of interact with each other to create this perfect sort of cocktail, of events that will increase this abundance of harmful algal blooms. So as it pertains to chlorophyll, when there's an abundance of nutrients in the water, there's an overabundance of algal blooms. I mean, they need these nutrients to feed, and if there's an overabundance, they will continue to propagate. But of course, chlorophyll can't be created without the presence of increased sunlight. And understanding the diffuse sunlight that's occurring in the ecosystem is of great importance to understand how that then impacts the abundance of chlorophyll. And then finally, warmer water, it really just creates a perfect environment for these harmful algal blooms to thrive and overpopulate. So we think of chlorophyll and light as positive things, and usually they are, but there's such thing as too much of a good thing. So I think when you're analyzing, harmful algal blooms and how they come to be, it's a combination of dissolved oxygen, chlorophyll, temperature, and we call it PAR, diffuse sunlight photosynthetically active radiation. So a little bit of everything at play there.
Great, thanks. I'll take a couple quick ones. So how many of these devices can be attached to one smart mooring system? For the smart mooring systems that we build and configure, it'll be 3 to 4 sensing nodes, depending on the configuration. It is possible to attach multiple sensors at a individual mooring node. And it is also possible to construct your own moored systems that can have many more than that. So there is no cap in terms of the total number of modules that Bristlemouth can support in a network. It's designed for up to hundreds of things to work on the same network. Spotter is a really lightweight, low power platform, so it's going to run out of power and data bandwidth far before you hit the cap of the size of system that you could plug in one of these new sensors to, but around 3 to 4 nodes on a spotter smart mooring. And then if you already have a spotter, can we add one of these new modules to it. Yes, if you already have a Bristlemouth capable spotter, then these new sensors will be compatible with that existing system. And then Chris, I've got one for you, which is if you can speak to how you would recommend configuring Borealis for an offshore wind site and some of the considerations that go into how you'd want to physically configure it and then maybe how you'd want to evaluate the data coming from that system.
Perfect. Yeah, I mean, it's an application we've got a lot of experience with at AOS. You know, for offshore wind, for those of you guys who don't do a lot of work in that space, there's a couple of things that you might use devices like the Borealis to monitor. First of all, you have to monitor what your acoustic emissions are. In Europe, in most of Europe, sound is classified as a pollutant. It is not yet in the United States, but there are still limits to how much sound you can make. When you're driving piles for the systems in shallow water, or when you're doing the mooring work for the deep water systems, you make a lot of noise and you're required to monitor how much noise you're making, both during construction and then also after the installation of the facilities. So for monitoring your own noise, you need a hydrophone that has an enormous dynamic range, so that you can monitor, the whole range of possible sounds that can be generated. And then the second thing that you need to do is monitor for the presence of marine mammals, and particularly endangered species like the North Atlantic right whale, for example, off of New England, in the presence of construction. And depending on the permitting and the specific rules in your area, you might be required to, for example, shut down construction entirely, if the presence of like a highly endangered marine mammal like a North Atlantic right whale is detected. And there are some companies that do this work a lot. We do business with them. Again, the Borealis system should be pretty darn useful for that application because, you can run your own software. If you have a detector classifier library on the SBC, you can have it be triggered if something is detected, so that you can run your detectors and classifiers. If you're interested in doing that kind of work, there's a company AOS works with a lot called Jasco, who we absolutely love, and we've run their software on things like Raspberry Pis at the edge with mature detector classifier libraries, and I think they've had good experiences with it.
Great. All right, let's. I'll handle some of the quicker ones. So how do we typically get data from the sensors? So Spotter is equipped with a global IoT cellular as well as satellite data. So if you're near cell range, you can use the cellular, which is much more bandwidth, much lower cost. The satellite data is available everywhere with very low latencies for global satellite data. So on the order of tens of seconds of latencies anywhere around the world, but you pay for that. There are other telemetry in the works. I know, Chris, you all at AOS are certainly looking into higher bandwidth options because acoustic data is so much richer than other sensing data. We would want to send a lot of bits out if we have the ability to do so. Is there an easy way to access this data on the Sofar dashboard or API? Yes, so both of these sensors will have full integration into the API and dashboard, which will include the persistence of all the historical data, nice APIs for being able to slice and dice that however you need to, and then dashboard visualizations that will help for operational use cases, system health monitoring, and understanding at a glance what's going on in the systems. Chris, we have a question on acoustic tag receivers for animal tracking. So the question is, can the AOS hydrophone interpret that signal? And I'll augment that to what is the path to that if it can't today?
It depends on the tag. If for very short range stuff, they can get pretty high frequency. But all of the tags I've ever worked with, yeah, that'll be within the bands that we can work with. So I think right now, out of the box, it would be pretty appropriate for monitoring those types of tracking tags. I'm actually hoping to work with a group of researchers down in Baja California, Mexico, who track Mobula monkiana, the monk rays. And I'm hoping to try to deploy a few of these units in order to try to track their tagged animals. So from the specifications, it absolutely should work, and I'll let you know if it works in a few months.
All right, for some follow-up questions. So for cellular, there is a long list of networks, compatible networks and bands. So it's a broadband cellular. It works on old 2G stuff that's still hanging out in some corners of the world, as well as the newer LTE bands. And there is a lot of different networks around the world that we can support. Reach out to our sales email for details on if it will work in your particular locale. And then we have a question on, is there a spec sheet for the Borealis? Yes, we have a preliminary spec sheet, which details that Chris shared in his slides. You can reach out to sales for that as well. These specifications are going to be finalized in the near term. If you have any questions on ones that are particularly relevant to your application, which you might decide to wait on or not for a pre-order, don't hesitate to reach out to us and we can provide detail on that. And then we have a couple questions on ease of deployment and maintenance for a spotter and smart mooring system. So I'll kind of lump those together. And so we're making this system as easy to deploy as we possibly can. It is still the most difficult aspect of any marine system. We want to make sure that that is where we're putting as much of our focus on making these systems more scalable and accessible. So we have people, this is not a recommended method of deployment, but we have had people put on a pair of fins and a mask and swim one of these things out where it needs to go and drop it in the water. We've had people deploy these off of small craft. It is not intended that you need any type of mechanical deployment support, so winches and cranes. Recovery can be more challenging depending on what your anchoring solution is. So we don't provide anchoring solutions, and there are different needs and regulations around what can be left in place or needs to be recovered. If you're using dead weight on sand, you might need hundreds of pounds of anchor for a large system, and that then is pushing the bounds of what can be recovered by hand without something like a winch. So it depends, but we're focused on making it as simple as possible in a different category of operation than what is typically done with large systems today. And then frequency of maintenance, the regular maintenance that is required is, depending on your area, biofouling will eventually start weighing the system down, start growing up over the solar panels. If you have plenty of solar power available, you don't have to worry about it that frequently. If you're in a really bioactive region that is at high latitudes, you might need to go clean those panels every 3 to 6 months. For all of the moored and cabling elements, we are designing those to last maintenance free for at least a year. Though, of course, depending where you're deploying, anything can happen. It can get hit by a boat, a big storm could lift your anchor and throw the system into the rocks, so your mileage will vary. And then let me look at some more questions here. How do the sensors on the mooring line transfer data to the surface buoy? So they transfer data over the Bristlemouth protocol. It is a 2-wire protocol, so there's only 2 conductors, which makes it electrically and mechanically very simple. You could do it over 2 coat hangers, and both power and data are modulated on those 2 wires. The data is all IP, it's internet-based data. And I think the remarkable thing is that today we can run this full IP stack on microprocessors that cost singles of dollars, and there's one of them in each of your headlights and your light switches at home now. It's just amazing the spread of these industrial grade, very low cost, very low power microprocessors that allow us to make very intelligent things. So everything on the Bristlemouth network has the ability to speak in this peer-to-peer network. You can interrogate what the interfaces are, so you can plug in and understand what data something produces. You can look at endpoints, so I can steer data to the SD card, I can steer data to satellite. It's a very developer-friendly way of exchanging data, and it also ends up being very flexible, which supports this kind of plug-and-play activity. And then Austin, I've got one for you. Can you speak to the calibration ranges and accuracy for the DO sensor? There's a specific need of 0.2 milligrams per liter of accuracy to understand hypoxic conditions. And so they're looking for a calibration range of 0 to 5 milligrams per liter. I don't know if you're able to answer that directly here, or if they should just email you all for more details.
Yeah, as it pertains to the calibration range, I would probably defer to Peter. He is our lead product engineer on this project. But a good way to get details on that end would be emailing info@pme.com.
Okay. All right, just cleaning up some of these questions. All right, what is a typical lead time for the spotter and sensor? So our lead times for spotters and smart moorings are 4 to 8 weeks. These sensors are not going to be available until next year. So you should reach out to our sales teams for specific timing as we are filling up the pre-order batch. The delivery for the next order kind of bumps down the line, so I can't give you the exact timing of delivery right here. All right, another one, is it possible to equip a multi-parameter sonde? So, you know, I think long-term PME's approach of focusing on an individual sensing element and really dialing that in and nailing that is going to be the way that marine sensing evolves. That being said, not all of the sensors that you would want are available as individual capabilities on Bristlemouth yet, and so there is a need for integrating with existing sondes, or maybe there are applications where you really do want the compactness of a sonde. So we don't have that as a commercially available option off the shelf. However, there are numerous groups that have successfully integrated and deployed multi-parameter sondes. There are documented examples and open source code using the Bristlemouth development kit. So if you have a sensor and if you've got the will and a little bit of skill or enough motivation in writing Python and wiring things up, you can connect any sensor that you want to Bristlemouth using the development kit and be able to use it in a application at smaller volume. So if you need to get 10 of something in the water to solve your problem, you can make that happen. And there's a whole community of developers and dedicated engineers who can support you as much as possible in doing that. All right, and then we got one more question specifically following up on LoRa. So LoRa is a long-range mesh wireless technology. It's kind of like Wi-Fi, but lower bandwidth and much greater distances. We don't commercially support LoRa today. We have done projects that integrate LoRa, and we are interested and open to discussing those. But you need to reach out to us so we can understand your use case a little bit more, and we can talk about options of how you might integrate LoRa into your system. All right, and that is all of the questions we have, and we're almost right on time. If somebody wants to sneak one last in, here we go. What data protocols does Spotter support? So Spotter, from a sensor connection protocol standpoint, it supports Bristlemouth. So if you want to get data into Spotter to use as telemetry or logging, or get power out of Spotter to be able to continuously power your sensor using the solar panels and battery Spotter, it goes over Bristlemouth. And that data protocol is it's a publish subscribe protocol. So it's kind of like JSON and internet rather than RS-232 or 485 or 422 or low-level serial protocol. So it's much more human readable. You can get moving much faster in these higher level protocols. You can use Python, you can use embedded C if that's your jam, but yeah. When do we plan on adding a hydrophone to a Sofar buoy off of Ocean Beach? Next week, Chris?
I mean, we did it in Long Island Sound today, so yeah, I think next week.
Yeah, literally, we're going to be doing that next week.
Yeah, it will be this one.
There's a clarification on the data protocol. So for data transmission, so the data transmission from the spotter out over telemetry, we have to rely on the protocols that the telemetry providers support, which are varied. From the back end to other systems, there's a set of RESTful HTTP endpoints that will deliver JSON or binary compressed data, and then there's a webhook style interface for receiving synchronous event data.
And Evan, real quick, I got some insight as far as the question pertaining to calibration range. So a newly calibrated microdot RDO integration, it should be accurate to about 0.1 milligrams per liter, in the range of 0 to 5 milligrams per liter. So the accuracy over that range ends up around 0.2 milligrams per liter after a few years. So essentially the microdot would fit that application based on what we've seen with the accuracy with the mini dots, with our previous experience.
Excellent. Thanks, Austin. All right, and with that, we'll address any of the other questions in a follow-up offline. Austin and Chris, it has been an absolute pleasure to work with you all and the teams through this. Thanks so much for joining today. Very excited to start getting these things in the water together and looking forward to putting them all over the world next year. Thanks everyone as well for attending, and stay in the loop on our social media and email lists for future events like this.
Thanks, Evan.